Assalamu alaikum. My name is Mobeen Malik and the circuit I'm going to implement in front of you today is a converter that converts a 4-bit BCD number to its 4-bit access 3 form. This circuit is basically a BCD adder that adds the BCD form of 3 to the decimal to convert them to a new number system. As you can see from the truth table, values in access 3 are obtained by adding 0011 to each of the decimal number. Like here, as an example in front of you, we have the number 0000, which in decimal form is 0. So if you add 3 to 0, the number becomes 3 in decimal form, and the BCD form of that 3 is 0011. And also in an example here where the number is 40100, this corresponds to 4 in decimal form. Now if we add 3 to 4 in decimal form, we get 7, and if we add the BCD form of 3 to this number, we get 0111, which is the BCD form of 7. So this proves that BCD to the access 3 converter is basically adding 3 to the BCD form. The circuit right here is implemented using self-made 5x1 muxes, as I was not able to find a proper 8x1 IC in Proteus. To accomplish this circuit, rudimentary logic was used that reduced the normal 10 inputs to a total of 5, hence reducing the complexity of the circuit. The mux, as shown in this child sheet, was made using 5 AND gates, outputs of which are connected together right here through OR gates, which then give out the output right here. Now if we go back to the parent sheet, I'll show you how the circuit actually works. Now these 4 are basically the 4-bit inputs. This is the most significant bit, while here is the least significant bit. Now if we see the rudimentary logics I've made from this truth table right here, you can see that Z is basically just the NOT of D. Now I have implemented it using a simple NOT gate, output of which goes right here through this bit, which is the Z. Now the mux for W is right here, for X it's here, and for Y it's here. They are placed sequentially, so it's easier to understand. Now the logic for Y is D prime, D, D prime, D, D prime. I'll show you how I got to that conclusion, this conclusion right here. Now if I divide the outputs in 2's, because a switch can either be on or off, so the Y at first here, these 2 inputs are basically the NOT of D. So which means that if the D is 0, the Y is 1, and if D is 1, the Y is 0, no matter what the output right here is. Now for the next 2 inputs, we can see the Y follows D. From the next one, the Y follows the NOT of D, and so on. Here again is D, and this again is NOT of D. This is how I get the logic. And if I explain to you X and W2, X, first 2 of the X follow D, the second 2 is permanently 1, which I have given through right here. This is the permanent 1, and this is the permanent low of 0. Now after these 2 are given 1, the next output is given the NOT of D. Here this follows the NOT of D. This is permanently 0, no matter what the value of D is, and this again is just D, as the rudimentary logic says. Now these are implemented on the circuit as follows. These are the 5 states that will be given to a single mux. Now if we see from here, the first input of Y is D prime, which means the NOT of D has to be given to the first input of Y. This is the mux of Y, and the first input right here is given the NOT of D. And that is basically how the whole circuit is made. A, B, and C will be used as selection pins that will be used to control which one of the following input has to be shown at the output. Now let's run the circuit to check its viability. If we use the input 4, which is 0, 1, 0, the output circuit should show 0 and 111. So if I do it like this and run the circuit, it shows 0 and 111. Now if we change the input to, let's see, 0110, which corresponds to 6, it should show 1001. So in the Proteus, if I do it like this is what it shows. That this actually shows that the circuit is implemented successfully. If I do it for 9, it shows this number corresponds to actually 12. So this was the BCD to access 3 circuit. I hope it helped you understand something. Thank you and Allah Hafiz.